Okay, I'd like to welcome you to the fifth lecture of the model checking class. Today's topic is linear time properties, but before we come to that, I would like to give you the feeling that it's not entirely theoretical what we do here. And I was recently made aware of some research that was being done at Microsoft by a former colleague that did his PhD on formal methods at our university. And what they do, it's not entirely what he did in his PhD here, but what he does now is he tries to make life for programmers easier. So he writes tools, and in this specific case, he wrote a tool that tries to analyze source code and guess whether the developer used the wrong variable in some place. And essentially the method builds also on program graphs, annotated program graphs, and so on. So you may think of program graphs as some theory structure, but it's actually used in practice. I mean, Microsoft, maybe you've heard of that company at some point. So it's actually being used in practice. Okay, so let's move to the lecture for today. Before I dive in, I want to tell you that I am colorblind. And the slides contain a lot of colors. So if I'm, calling the colors incorrectly, it's me, not you. That is confused, but I hope you can still bear with me. I will try to make it very explicit what I'm referring to, okay? Okay, so when we want to talk about linear time properties, it's the first time that we ever talk about properties in this course. Until now we've said, well, X is a transition system, Y is a transition system, everything is a transition system. But, model checking is about checking properties on these transition systems. So we somehow need to formulate these properties. And to do so, we're going to first talk about what is called the state-based and linear time view, because the linear time view will be the first view on transition systems we're going to study in this lecture series, but it's not going to be the only one. There's going to be a second one that I will be alluding to during this presentation. So recall the definition of a transition system. We have states, we have actions, we have a transition relation, we have some initial states, atomic proposition, and a labeling function that attaches labels to states. More concretely, it assigns a subset of the atomic propositions to every state, okay? And in the course of this lecture series, we're going to say, or make the following assumption. We're going to say that the actions, these are the things that you have along the transitions, they are used exclusively for communication, i.e. parallel composition of transition systems. Right? We're not going to use them in the properties. What we are going to use in the properties are these two components, AP and L. So we're only looking at the labelings of states when we're talking about properties in this lecture. Okay? Well, I just lied to you because there will be an exception to this in the future. When we're talking about fairness assumptions, we're also using this to some extent in properties, but this is going to be the topic of a future lecture. So for now, forget about the actions for the properties, only consider the labelings of the states. And to make this formal, you can think of the transition system as a graph, essentially, that has the same state space, but the edges in the directed graph are just without labels. So we're going to drop the labels when we talk about properties. Okay, so some notions, some of which you have already seen in the exercise sheet number 1. We're going to use standard notations for graphs. So we use post of S to denote the post image of the state S, meaning it's all successive states of state S. So if you think of the state S, then it has some outgoing edges in the state graph, unlabeled, and they lead to some successor states T. And these are put in this set post of S. And similarly, we have pre of S. It's the pre-image of the state S. It's all predecessors that can go in one step to the state S itself. Oh, and by the way, I didn't say this explicitly, but if you have any questions, just feel free to interrupt me, okay? Also, you already saw this on the exercise sheet number 1. We're looking at execution fragments or executions of a transition system. So what's an execution fragment? It's a sequence of transitions from the transition system. So it's a state, action, and so on sequence. It may be infinite or it may be finite. It may stop at some point. It can stop at any point. It's just an execution fragment. It doesn't need to be maximal yet. Okay, so, but as I've told you, when we're talking about properties, we're going to abstract from the actions along the transitions. So what we're going to do is we're going to project execution fragments to path fragments. So we're just going to drop all the actions in between and just look at paths as sequences of states that are connected via the transition relation in our transition system, or state graph if you want to. Okay. Now, additionally, there are two properties that execution fragments and path fragments might have. They might be initial. Well, what does that mean? They start in the initial state. So the first state of a path and the first state of an execution fragment may be an initial state. And in this case, we call the execution fragment and path fragment initial. And secondly, we can call it maximal. When do we call it maximal? Well, intuitively, it means you have to proceed as long as you can, meaning you may only stop in a terminal state, or you may never stop, right? So talking about execution fragments and path fragments, they are either infinite, if they are maximal, or they end in a state where you strictly cannot move on. And now, given these notions, we can define a path. Not a path fragment anymore, but now a path in the transition system T. Well, what is this? First of all, it's a path fragment. So it's a sequence of states that are connected via the transition relation of my transition system. It starts in the initial state, and it's maximal. So it's either infinite or it terminates in a terminal state. And this is what we call a path of the transition system. And because that will come in handy later, we're also going to formalize what is a path of a state. And intuitively, we're just going to drop the initial here and require that it starts in state S. But otherwise, it's the same. It's still a maximal path fragment, just starting in some specific state S and not in some initial state. Okay? And we're going to use these notions a lot. So paths of T, for T being a transition system, just denotes the set of all paths that are possible in a transition system. And likewise, paths of S denotes the set of all paths that are possible starting from some given state S in the transition system. Okay, so let's move on and maybe ask you the first question of today. How many paths does this transition system T have? Yes? You would say 3, okay. Okay, let me know which paths are you referring to?
Going from S0 to S2 and going from S0 to S1.
Yes.
And the state is S1.
Exactly, but my reasoning would be that it's...
There are infinite paths, I would say. You can choose any finite path from S1. So you go to S1 twice, 4 times.
Exactly, so you both are right. But you should note it's 2 because we said that a path is maximal, right? So the path from S0 to S1, you cannot just stop there. So you need to go on. So there are 2 paths, as you said, from S0 to S2. That's a finite path, if you will, or yeah. And from S0 to S1, but then you need to go on, so you infinitely often have S1. Okay? So it's 2 paths in this transition system. Good. We may also look at the paths of starting in some specific state, and in this case, let's just pick S1. And that's somewhat boring because there is only one path starting in as 1, which is just repeating as 1 infinitely often. You just have to keep going as long as you can, but there is no other choice than choosing as 1 as the successor. So it's just as 1 infinitely often. Now we're going to extend this. We're also going to look at finite paths, or denoted with path subscript fin, starting in some state. And these are the set of all finite path fragments that start in the state as 1. Okay? I want to stress here that the finite paths here are not maximal. Okay? So it just says it's a finite path fragment. Path fragments may stop at any time. Okay? So this does not mean that it's the paths of S1 restricted to the finite ones. No, because paths always need to be maximal. But it's really just the finite path fragments can stop at any point in time. Is that clear? I see a slow nods, that's good. Okay, so now we've discussed what we understand under the state-based view of a transition system. So we just look at the atomic propositions and the labelings of the states. Next, we're going to take a step at what is called the linear time view. Well, as I said, there are two views, two computing views, and historically speaking, there has been quite a philosophical debate about which one is better. We have no opinion on this, but just say we're going to show you both, and they are both interesting in their own rights. Okay, so remember we have a transition system. We take the state-based view, so we abstract from the action, so we effectively have a graph and a labeling of the states of the graph. Now there are two views. One's called the linear time view, and the other one is called the branching time view. And the name already suggests what they are referring to. So in the linear time view, you look at the behavior of a transition system by just looking at paths, right? You just look at state sequences all the time. You know, effectively, you're not looking at the branching structure of the transition system. You can only look at linear paths. This is different in the branching time view. In the branching time view, you also account for what kind of non-deterministic branches are there in my transition system. And we're going to see an example on the next slide. So let's look at our beverage vending machine again. And this is a machine that, you know, initially you can pay it some money. So there's a coin deposit where you can put in a coin. And after you have put in the money, you can select either Coke or Sprite, and then you get the drink, and then you can repeat that. Well, what about this other vending machine? It looks similar, but is still somewhat different. So initially, we pay, but we have to already pick one of two coin deposits. So there are two slots for our coins. So one of which, when you put in the coin, you will only get Coke in the end, and one of which you will only get Sprite. So you have to already make up your mind before putting in the coin. So let's extend that to, say, proper transition systems. So we also have actions along the transitions, and they are also more or less the same in both transition systems. So when you get a Coke, it's labeled with take Coke. Selecting Coke is better, and so on. But as we said, we want to abstract from the actions along the transitions in the state-based view. And what I haven't told you before, but this will also be the case, we're going to project the paths or the states to atomic propositions, to their atomic propositions, to their labeling. So that means that states are indistinguishable that have the same labels. Okay? So let's do this. Let's do this here. So let's assume we have the atomic propositions Coke and Sprite, and we're going to label the Coke states, so when we have selected Coke with the atomic proposition Coke, and the Sprite states with Sprite, and the other ones are labeled with the empty set accordingly. Okay? Then our assumption is you cannot distinguish between these states. You can only look at their labels, and otherwise they are the same. They have no identity. And same thing here. Okay, so let's look at the linear time behavior of those two transition systems. And as you might already see, they are not distinguishable in linear time. If you look at all the paths going through this transition system and project this to the colors, right, that correspond to the labelings of the states, you will get a sequence like this. So you get empty set, Coke or Sprite, empty set, Coke or Sprite, and all paths that you can select in this transition system, they look like this. But that's the same in the right transition system. So you always get empty set, some drink. Then you go back, empty set, some drink, and so on. So the paths, or the labelings of the paths, are the same in linear time when you look at just paths. But I can tell you, in branching time, these two transition systems would not be considered the same. Can you imagine why? Okay, so I'm going to tell you. In branching time, the left transition system is different from the right because there is a state here that has two distinguishable states. And you look at the branching structure, you can, in branching time reasoning, you can see what is the branching structure of my transition system. And since you can distinguish these two states, you know that this state up here has two different, with respect to their labelings, successor states. And this is not true in the transition system on the right. Okay, but we will talk about branching time view later quite a bit. Okay, let's choose some different atomic propositions. Let's say we're not interested in what kind of drink we get, but we're interested in what states you needed to pay. So when you label the states accordingly, they look like this. And now, for these two transition systems, linear time view and the branching time view coincide once again. Well, why is that? Because here, we cannot distinguish the two successors. They're both labeled equally. They are, in our view, they are the same. So also the branching time will only observe, like, pay, empty set, and then have some drink, and then repeat the process. Okay. Okay, so we've just seen that coming from a transition system, we first abstract from the actions, arrive at the state graph plus a labeling function of the state, and that there are two different views on how to interpret the executions or paths in these transition systems. And what we've done implicitly is we projected onto the atomic propositions of the states. And we're going to formalize this now. So in the linear time view, this gives rise to the notion of traces. So from a path, we can obtain a trace by essentially projecting onto the atomic propositions of the individual states of the path. And here, this is going to be a bit more complicated because you also need to account for the branching structure, so you will intuitively have some kind of tree there. Okay, but now, for the rest of this lecture and also for the rest of the, I don't know, next 5 lectures or so, we will talk about the linear time view before moving on to the branching time view. Okay, so let's talk about traces. We've already seen that executions are sequences of states and actions of my transition system. They can be infinite or finite. We have seen paths. These are the projections of executions only to the states. And because executions can be infinite or finite, accordingly paths can also be infinite or finite. And if you take this one step further, you can project such a path as 0, as 1, as 2, and so on, just to the sets of labelings along this path. And this is what we call a trace. Is this clear to you? Okay, very good. Now, what do we have then, formally speaking? Well, it's a sequence of labelings. And since it can be either infinite or finite, can be an infinite word or a finite word. So either it's a finite word, meaning it stops at some point, or the trace goes on and on and on because the underlying path goes on and on and on, and then the trace will be an infinite word. Okay, but this is a bit ugly, so we have to have both infinite and finite words, so we don't want this. And one assumption that we're often going to make is that we say, let's get rid of all terminal states in our transition system, right? Because what happens if we don't have any terminal states in our transition system? It means that there are no finite executions, right? So we can just cross this out. But if we have no finite executions, then we have no finite paths. And if we have no finite paths, then we have no finite traces. So we're going to often assume that all the traces, all the paths, all the executions are just infinite. And why can we do this? You could say, well, you know, what if my transition system has actually terminal states? What are we going to do about it? Well, there are actually two cases then. One case is the terminal state in your transition system represents some kind of intended halting configuration. So say you have a program graph and you translate that into a transition system. And yeah, your program terminates at some point. So it's fine to not be possible to go on then. I mean, it's kind of intended that your program terminates, potentially at least. Well, what do we do then? We're going to modify the transition system slightly by adding a transition from this terminal state to some kind of special stop state that indicates, well, your system has terminated properly, if you will. Right? And by equipping this state with a self loop, you already see that we've got rid of the terminal states that fall into this category in our transition system. And then the second category is that, well, you didn't want this state to begin with in your transition system. You don't want it to be terminal, but then you should fix it, right? Because potentially it can be a deadlock in your system and you don't want deadlocks, for example, and so on. But then you should refine your design before moving on, right? So given this reasoning, we're going to assume no terminal states in our transition system. And if you have some, we can get rid of them somehow. Okay, just like we gathered all the paths into sets for a transition system T, we're also going to assemble all the traces of transition system T by taking all the paths that go through the transition system and projecting them onto the atomic propositions along the path. And similarly, we do the same thing for finite paths. So we take finite paths, project them onto finite traces, and gather them in the set traces with subscript fin of the transition system T. Okay, and recall again that a path in the transition system is a path fragment. So it's a sequence of states. It starts in the initial state, and it's maximal. You need to proceed as long as you can. And here, you drop this maximality and you restrict to finiteness, right? So finite traces can stop at every point, whereas infinite traces, they need to go on as long as possible. Okay, and if you decide to assume that there are no terminal states in your transition system, you can drop the maximal here, but just write infinite because a trace will be infinite or a path will be infinite if and only if it's maximal. Yes?
What would be the labeling for the last state with the infinite?
It could be, for example, some kind of special label terminated properly or something like this. And then as we're going to see later, we can talk in properties. We can reason about these labelings. So you could, yeah? No, it depends on the context, really, how you resolve this with the terminal states. We're just assuming that you can somehow deal with it. In practice, you would probably label it with a special new label and say, for example, all paths through my system eventually reach this state, for example, or something like this. Okay? But the point I wanted to make is not a real restriction to say we don't have terminal states. You could also lift all that I'm going to show you to transition systems with terminal states, but it's just a mess because you always need to account for finite words along the way. And which is why we say we don't want that, we want it easy, so just use infinite paths. Okay, and again, the traces are infinite words over the superset of atomic propositions. So this is every element of this word is a set of atomic propositions, and the finite traces are obviously finite words, but over the same alphabet. Let's look at an example. So we have a very simple transition system here. It has a single atomic proposition A. So we have one state labeled with this atomic proposition, and the other one is just labeled with the empty set, which is also an element of the power set of the atomic propositions. Okay, so what are the traces of this transition system? I mean, the definition is right there. So, maybe what is one trace in my transition system? Yes?
Blue and yellows.
Exactly. So one trace in my transition system is starting in this state, so you get an A. So you don't see the state, but you only see blue, as you correctly said. And then you move on to yellow infinitely often. So that's one trace in this transition system. Is there another trace? Yes? Yellow infinitely often, because this state is also an initial state. Okay? And in fact, these are the only two traces in this transition system. Let's move to the finite traces of this transition system. What are the finite traces? Or what is one finite trace? Exactly. And this is exactly what is written here. It means that, you start in either of those two states. So let's assume it is this one, then you start with an A, and you can stop there. So you just observe blue. But you can also move on to see an arbitrary but finite number of yellows. But you can also start in the yellow state, in which case you will see at least one yellow, but then can go on to see an arbitrary follow-up numbers of yellows. Okay? Is this clear? Because that's all important. It's going to be the basis of the next lectures. Okay. Good. Let's look at some mutual exclusion algorithm, some example. Let's do not dive into the details, but let's just see that it follows the same structure as we had before. So there is a non-critical section for two processes. They can decide to wait in order to enter the critical section. Both processes can do that. And they have a critical section that they both must not enter at the same point. And then if you look at the transition system for this program, for these two program graphs that I've just shown you, it looks like this. Right? Now let's assume the set of atomic propositions is given by crit 1 and crit 2, because you're interested in whether this algorithm actually establishes mutual exclusion. Yes?
A quick question to the last slide.
Yes.
One for that even.
Yes.
Is the empty set also a finite trace?
Yes. Yeah, but one, exactly. One empty set, so one yellow is in here, right?
You know the empty path, I mean, it's an empty trace basically. Because you
No, because we said paths need to start at some state, so they include the first state of it. It's
okay, because it says finite trace and then there's a star instead of a plus.
That's still true, but technically I think you could write a plus there. You're right. But yeah. Yes.
What if a state has two labels? How would you write that?
So the elements of your traces, they are sets. So you might just as well say it's the set containing A and B. This is one element of the alphabet that gives rise to this word. Okay? So it's perfectly fine to have multiple labels for a state, because every element of the word, every character of the word is a set of atomic propositions. I mean, we already have that here. I mean, it just contains one element, but why wouldn't it contain 10 elements or infinitely many elements or something like this? Okay, does that answer vaguely the questions? Okay. Okay, let's look at the transition system of the semaphore-based mutual exclusion again. We have two atomic propositions, crit1 and crit2, because we're interested in mutual exclusion, whether this algorithm establishes it. And then the labeling is graphically represented like this. All the states up here, they don't have any label because neither is process 1 in the critical section nor process 2 is in the critical section. Here we have process 1 in the critical section, and like symmetrically we have process 2 in the critical section over here. So let's look at the traces for this particular example. Well, one trace that you can obtain is, because you can only start in this state, is empty set, crit1. Empty set, crit1. And repeating that forever. That gives rise to this trace, and this thing, this infinite word, is part of the traces of this transition system. Okay? Now let's look at a somewhat more complex trace. Let's look at how it proceeds. So we take the following path. Starting from this state, we observe empty set, no labels. Move there, again empty set. This state, again empty set. Now we move to this state. Well, this state is labeled with crit1. So we have this element down there. Then we take this transition and have again empty set, move to crit2, and observe crit2, and so on. And you can step through the transition system, and like this you basically obtain all the possible traces in your transition system, okay? Good. Let's choose another set of atomic propositions. Say we also have crit1 and crit2 as before, but now we also have whether the processes are actually waiting to enter the critical section. And then you have the following labeling. This state down here is actually labeled with wait1 and crit2. It's the only state that is labeled like this because we have more atomic propositions. And now the traces, of course, are different than before, right? Because the atomic propositions that you use to label your states, they clearly have an influence on the traces of the transition system. And now we have a trace that looks like this. Empty set, wait1, just wait1. Then, and that answers your question, you can also have a set containing wait1 and wait2 along your trace. And then going to this state, you have wait1 and crit2. And then you basically repeat that by going infinitely often through this loop. This is one trace if you, for the transition system when you change the atomic proposition slightly. Okay, now we've discussed what is called the state-based in linear time view, but we still don't know what is a linear time property. And this is the next thing we're going to do. We're going to define it. And then the rest of the lecture, and actually also the full next lecture, is dedicated to categorizing linear time properties into important sets, subsets of linear time properties. Okay, this is a picture you're going to see quite a bit in this lecture series. It's basically showing you what model checking is about. You have a system consisting of some parallel processes that gives rise to some transition system. You have a set of requirements. You somehow, we don't know yet how to do that, but we somehow derive a formal specification from that. Then we want to derive algorithms so that we can invoke our model checker, and it tells us, yes, your specification is satisfied on your system, or it says, no, it's not satisfied, and it gives you an error indication or counterexample. It shows you, well, this is wrong about your system. This is why the property doesn't hold. And in the first lectures, you've seen how we can basically write down such processes, such parallel processes, and using structural operational semantics rules and an abstraction from the actions can derive the state graph, or the transition system, essentially, from these parallel processes. So this is what we have already seen, and now we're talking about the right-hand side a bit more. We're going to talk about what could a specification look like, and in particular, we're now going to look at linear time properties that are able to capture certain behaviors. Okay, so what is a linear time property? A linear time property is nothing else than a set of infinite words over the alphabet 2 to the AP, right? So if you give me any language of infinite words over the atomic propositions of some transition system, then this is a linear time property. We're going to see why we can think of this as being a property. So again, a linear time property is just a subset of all infinite words over labelings of states, essentially, atomic propositions. Is that clear? Well, okay. So let's look at an example. Say our set of atomic propositions includes crit 1 and crit 2. So we again are talking about some kind of mutual exclusion algorithm or something like this. How can we formalize the property mutex that says mutual exclusion holds? Well, we can do that by saying, well, let this set of infinite words, let it contain all infinite words of the form A0, A1, and so on, over the power set of atomic propositions, such that for every AI, we have that either process 1 is not in the critical section or process 2 is not in the critical section, right? So all these words are characterized by the fact that none of them contains crit 1 and crit 2. No other restrictions apply. But no AI along this infinite word contains crit 1 and crit 2. Okay, so let's look at some example infinite words and whether or not they are actually contained in the property, in the linear time property. Let's look at this one. So it starts with an empty set, then has weight 1, only weight 1, only crit 1, empty set, weight 1, crit 1, and so on, continuing that infinitely often. And the point is that is contained in our property. Why is that contained in our property? Because if we look at every element along this thing, at no point will we have crit 1 and crit 2 in one set together. Let's look at a second example. Empty set, weight 1, crit 1, weight 2, crit 1, crit 2. Well, obviously, this is not in our property because there is an element, it's A0, A1, A2, A3, A4, that contains crit 1 and crit 2. So this is not an element of our set of infinite words that we called mutex. And finally, I want to remark that the words that are contained in this property, they don't necessarily need to make sense for your transition system. So for example, we could look at the following word, empty set, weight 1, crit 2. Well, you could say, well, what's this word about? How can process 1 be weighting n in its critical section? That somehow doesn't make sense. But the property that we defined here, it doesn't care about a transition system. It just says, what are the infinite words contained in this property? And this word satisfies the property that we wrote up here. So it is contained in the mutex property. Simple as that. Okay. What we just defined, the mutex property, is called a safety property. This is a very important class of property that we're going to talk about quite a bit. And the other important class that we're going to talk about is liveness. We're going to talk about that later in the next lecture, but just to show you that there are also more complicated, if you will, properties. Say we want to make sure that our mutual exclusion guarantees starvation freedom. Okay? What does that mean? We're going to formalize that in the property like this. It means, well, put in all the infinite words, A0, A1, A2, and so on, into your property that satisfy the following criterion. If infinitely often along the trace, process 1 waits to enter the critical section, so this AI appears along the infinite word, and if for infinitely many sets AI we have that process 1 waits, well, then we also want to have that it infinitely often enters the critical section. So for infinitely many points in time, crit1 is in one of these sets AI. This is not the only way to write down starvation freedom, but we choose that just in this context, okay? And similarly, we want to have that if process 2 waits infinitely often for the to enter the critical section, then we want to have that it actually enters the critical section infinitely often. But as you can see here, the condition that we specify here, it just talks about the individual elements along an infinite word. It doesn't talk about a transition system at all. It just says, given an infinite word, A0, A1, A2, and so on, what is the condition for me to put such a word into my property? Okay, now we've defined linear time properties. Sorry, was that a question? Okay. Now we've defined linear time properties, but we also need to define when does a transition system satisfy a linear time property, right? Because that's the core part. If we want to establish my system is correct, then I want to say my transition system satisfies some property, some LT property. And we're going to do that now. And how are we going to do this? Well, we say that a transition system, T, without terminal states, satisfies an LT property E, which we write like this. So T satisfies LT property E, if and only if all the traces from the transition system T are contained in the linear time property. What does that mean? That means whatever you can do in your transition system, no matter what, all the traces, so you take any arbitrary path and you project it onto the atomic propositions, and you must make sure that this trace, this sequence of atomic propositions, sets of atomic propositions, is fully contained in your property. Right? Because it somehow means that what your transition system can do, it's all safe. Because the property says these are the allowed behaviors, and all behaviors of your transition system are contained in these behaviors, so all behaviors of a transition system are allowed in a sense, or allowed with respect to the linear time property E. And because that will be convenient later, we're also going to define that for a state. So here we define it for a transition system, but very similarly we define it for a state. We say a state satisfies an LT property if and only if all traces, all the paths starting from S projected onto sets of atomic propositions are contained in the linear time property E. Let's look at an example. Again, mutual exclusion with semaphore. And first of all, I want to convince you that this transition system satisfies the mutex property. Recall that the mutex property said it contains all infinite words such that at no point we have that crit1 and crit2 are contained in the same labeling. And why is that trivially true in this case? Well, because there is no state labeled with crit1 and crit2. So no matter which path you take through this transition system, you will never encounter a labeling that contains crit1 and crit2. Okay, that was simple, but now let's talk about the liveness property we defined. So if infinitely often process 1 wants to enter the critical section, it infinitely often does so, and the same for process 2. Would you say it's satisfied or is it violated? Yes? It's violated? Why would you say so?
For example, it can stay in wait 1 and never get into the critical.
Exactly. And the reason is that we have the following trace and word. Let's look at how we can construct it from a transition system starting up here, labeled with empty set, neither crit1 nor crit2, and also not wait 1 and not wait 2. We go down there. So we record wait 1, go down there, have wait 1, wait 2, and then we follow this cycle of crit 1, wait 2, and just wait 2, and follow this cycle infinitely often. And as you can see, this thing is not contained in my liveness property. Well, why? Because we have wait 2 infinitely often, but at no point do we have crit 2, right? So if you will process 2 stars, it never enters the critical section. So in summary, this transition system does not satisfy the liveness property because there are traces in this transition system that are not contained in the set of infinite words that makes up the linear time property. Okay? Good. Okay, let's look at a different mutual exclusion algorithm. Again, let's not look at the details, but the structure is the same. Non-critical section, process 2 waiting, critical section, process 2, and so on. And if for this modified algorithm or other algorithm you write down the transition system, it looks like this. Well, again, you can see trivially that Patterson's algorithm, how it's called, satisfies mutual exclusion because there is no state in here that's labeled with crit 1 and crit 2. But this time, we also have that it satisfies the liveness property. And from the transition system, we can see it like this. So these are all the states that are labeled with wait 1. Okay? And we see that, from these 2 states, we will definitely have crit 1 as one of the eventual successors, right? There is no way to leave the set, essentially, of these 2 states without going either there or there. So you will have also crit 1 as soon as you had wait 1 in these 2 states. But then we see that this wait 1 state, its only transition was to this wait 1 state. And similarly for this wait 1 state, it could only go here. But then this means that this whole set where we have wait 1, it needs to have crit 1 as an eventual successor, right? So we cannot intuitively, if we follow a path through this transition system, we cannot infinitely often or infinitely long stay in these wait 1 states without ever going to the crit 1 states. Okay, is that roughly clear? Okay, let's talk a bit about trace inclusion. Well, this is just the definitions we had until now. So we have a linear time property E, we have a transition system, and we say the transition system satisfies the linear time property if and only if all the traces of the transition system are fully included in the linear time property. And as a consequence of this, you get the following implication. You take any 2 transition systems, T1 and T2, over the same atomic propositions. And you take any LT property E, really an arbitrary one. Then, if you have that the traces of the first transition system are fully included in the traces of the second one, and you have that the second one, T2, satisfies the linear time property, then this implies that the first one, T1, also satisfies the property. Why is that? Yes? Exactly. So it's okay, strictly speaking, the transition system is not a subset of the other, but you correctly identified that the traces of T1 are included in the traces of T2. This means nothing else if we look into the definition that the traces of T2 are fully included in the traces of E. And if you follow this chain, it also means that the traces of T1 are fully included in E. Okay, this is maybe easy to see. So this is the reasoning we just explained, so let's move on. But this was an implication, right? We said if you have this, then for all LT properties, you have this. You have that if T2 satisfies the LT property, then T1 satisfies it as well. But what you can actually show is that it's equivalent. You have that for 2 transition systems, T1 and T2, the following is really equivalent. The traces of T1 are fully included in the traces of T2. This is equivalent to saying that there is no LT property, or I should formulate it positively, that we have for all LT properties that if T2 satisfies it, then T1 satisfies it as well. Okay, so we have the connection between trace inclusion of 2 transition systems and a strong statement about some kind of property preservation, meaning that if the transition system that has more behavior already satisfies a property, then definitely the transition system with less behavior will satisfy it as well. And I mean, the direction from left to right, we just looked at on the previous slide. And for the reverse direction, it's easy to see if you choose the LT property as the traces of the second transition system. Now, why is trace inclusion relevant? Why are we even talking about it, right? I mean, it's a nice theorem, but what does it give us? And what I want to convince you of is that trace inclusion appears naturally in quite a number of areas. So we will go through these three items bit by bit. And the first one is it appears as an implementation or refinement relation. So let's say you're designing a piece of software, right? First, you're thinking about some requirements, and then you derive a specification from that, and you come up with an initial design TI that maybe allows a lot of behavior, and later on, you see that you want to refine the behavior, you want to restrict it in a certain sense. Well, in our case, the specification is an LT property E, or linear time property E, and say our design TI already satisfies parts of the specification E. Well, then typically you have that your follow-up design TI plus 1 is in some kind of relation with the design TI that captures that it still correctly implements the previous design. It only refines it. It makes it more precise, more concrete, more refined. And one of the implementation refinement relations you could look at is actually trace inclusion, right? So if you have a transition system as a design TI and you make it more precise, for example, by taking some transitions away, then your follow-up design TI plus 1, well, the traces of the new design will be fully included in the transition system of the previous design. Okay, and what does that mean? Well, as we've seen, it means that your follow-up design automatically satisfies your linear time property E if your previous design already did so. This is what the previous theorem essentially gives you. Okay, so if we look at a concrete example, again, some mutual exclusion algorithm, and let's say our design TI said, well, you can take both transitions here. All is possible. We don't specify what is happening precisely, and there is a competition in this state. And let's just say our more refined design says, yeah, I don't want that race. I don't want non-determinism in my system. I want to get rid of this transition and say we always give priority to process P1 in this state. Well, then clearly you arrive at a transition system if you delete this edge that looks like this. And it's clear that the traces of this transition system are fully included in the traces of the upper transition system, right? So you know by the theorem, if the first one satisfies an LT property E, then also your more refined one will satisfy the same LT property E. Yes?
Just a question. So if I have a trivial transition system without any traces, I satisfy all properties?
What is a transition system without traces? I would say there is no transition system without traces. I mean, you have to have states in your transition system because we define transition system to have a non-empty set of states. We said that we don't have terminal states. So like the minimal transition system would somehow maybe look like this, if you will, right? And there is a label attached to this state. There is a label attached to every state. Can be the empty set. That's perfectly fine, but there is some label. So there will be traces, right? And in this case, you will have traces, only one trace that has empty set infinitely often. And no, this will not satisfy all LT properties because I can exclude that trace, that one trace in this case, from the LT property, and then this transition system does not satisfy the LT property. Okay? Yes. I mean, we are not talking about state identities anymore. We already projected onto the labelings, right? So if the labels coincide, no matter what states there were, no matter how we came up with them, parallel composition, whatever, there are no identities to states. We only look at the labelings of these states. Okay, and since we have that the paths of the lower one are fully included in the paths of the upper one, in fact, for any set of atomic propositions, we have that if the above one satisfies a linear time property E, then this implies that the lower one also satisfies the linear time property, no matter what the LT property looks like. Okay, this was the first item where trace inclusion naturally pops up. The second one is when resolving non-determinism. This is somewhat similar to the first one, but let's still talk about it. So say you have some kind of transition system and you want to resolve the non-deterministic choices, right? I mean, in practice, if you implement a system, you typically don't want non-deterministic behavior. You want deterministic behavior. You want to say, okay, I have all my behavior of my system, but I want to find a strategy that is also meaningful in some way, that resolves all the non-deterministic choices. And if you apply such a strategy to a transition system, you will naturally come to a transition system that includes a subset of the traces of the original transition system. And finally, it pops up in the context of abstractions. So let me quickly illustrate that because I find it very interesting. It's not a major topic of the lecture series, I would say, but who of you is actually following static program analysis as well? Only a few hands, but you guys will definitely see something similar in that lecture. So say we have a program that looks like this. Initially we set x to 7, y to 5, then we have a while loop that loops as long as the content of the variable x is strictly greater than 0. And what does it do? What's the content of the while loop? Well, we subtract 1 from x and we increment y. Okay, and the question that we have is it possible that we somehow go through this while loop a number of times and then at some point arrive at L2 and have that y contains an odd value? Is it possible? Well, we would say no, it's not possible somehow, because here we have the distance between x and y is 2, right? And this loop maintains that the distance is always congruent modulo 2, if you will. Okay. Well, if you formulate this program as this source code, if you convert that to a program graph, it may look like this. So you have 3 locations that correspond to these lines, essentially. The most interesting one is L1, where you can either take the loop, the while loop, as long as x is greater than 0, or you may go to location 2 if x is less or equal than 0. Now, again, still we want to know, like formally, automatically derive that it's not possible to arrive at L2 while having an odd value in y. So we want to determine, is it true that the transition system that is underlying this program graph satisfies the LT property, never is it possible to reach location 2 while having an odd value in y. Well, what we could do is we built this transition system. But it may be infinitely large. Maybe it's not in this case, but imagine you have a number of integers and your program is larger, so this is only a fragment of your program. So the transition system might be large, it may be huge, it may be infinite if you look at unbounded integer variables. So it's maybe not the best idea to build the transition system and then verify the property. But what is often done is that you abstract first. So instead of remembering the concrete values of the 2 variables x and y in your transition system, you only remember the truth values of predicates. right? So in this case, we're going to take the predicates x is greater than 0, x is 0, or x is congruent y modulo 2. So that means that modulo 2, x and y are the same. Okay, and clearly if you only look at predicates, if you only remember predicates in your transition system, well then the transition system is finite, right? Because how many valuations, truth value valuations of these predicates do we have? Well, it's 2 to the 3, right? If you go through them. Okay, so let's look at the abstract transition system. What would it look like? And as I said, now instead of remembering the concrete values of the variables x and y, we only remember the truth values of these predicates. And then this slide tells you, well, we start at L0, set x and y to some values, but we don't remember them, right? So we just know that if we execute this line L0 and basically assign 7 to x and 5 to y, then we end up at L1, and we only know that x is greater than 0. We don't know that it's 7. We just know that it's greater than 0 because we abstracted with respect to these predicates. And we know, because it's 7 and 5, that modulo 2, they are the same. And if you keep doing that, if you keep building the abstract transition system, then this slide tells you that, taking the while loop somehow corresponds to taking the self loop. You still don't know the values of x and y, but you know that executing the loop body will maintain this predicate. Yeah? If it's true in the source state that x and y are congruent modulo 2, then one execution of the while loop will still have this. Now, this example is not entirely correct for a minor reason, I would say, because here in this abstract transition system that, to my opinion, is just wrong, you can go from L1, if x is greater than 0, directly to L2 with x is 0. That is not a behavior that is in here, right? First of all, you would need to go from L1, where x is greater than 0, to L1, where x is 0, right? This one step, executing the while loop and having x0 in the successor. So there's one state missing in between, but the overall message is still this. If you abstract with respect, for example, to these predicates, then you arrive at an abstract transition system. And then you can look at the traces in this abstract transition system, and you will see that the traces of this transition system is actually a superset of the traces in the original system. It over-approximates what is possible in the concrete transition system. And that means, remember the statement about linear time properties, that means if all traces in this abstract transition system are contained in my linear time property, if this abstract transition system satisfies my property, then so will my concrete transition system T. And this is effectively the bottom line of this slide. The details, I would say, they are not too important. The bottom line is trace inclusion pops up naturally when you abstract things. When you over-approximate things, it means you introduce more behavior. So the resulting transition system will have strictly more traces. Okay? Okay, let's take this one step further. Right now we had trace inclusion, but there's also trace equivalence, so that the traces of two transition systems are the same. So let's consider two transition systems, T1 and T2. And they are called trace equivalent if we have trace inclusion in both directions. So the traces of T1 are included in the traces of T2, and the traces of T2 are included in the traces of T1. Well then, what you can show is that trace equivalent transition systems satisfy exactly the same linear time properties. And that's not hard to see, so we leave it as an exercise to prove this. But similarly to trace inclusion, you get the following theorem that says it's equivalent that both your transition systems have the same traces. That is equivalent that for all linear time properties, you have that they satisfy exactly the same properties. Okay? Is this roughly clear? So if you have transition systems with the same traces, they satisfy the same linear time properties, because clearly, if the traces, for example, of T2 are fully included in a linear time property, then so are the traces of T1 and vice versa. And if there is a trace in T2 that violates some property E, well, then the trace is also included in T1 and it also violates the property. Okay, let's look at our beverage vending machines. I already hinted at that in the beginning of the lecture, that when we choose some set of atomic propositions, in this case pay, Coke, and Sprite, so it corresponds to this labeling of the states, then the traces of these two transition systems are the same. They are not distinguishable. And this is what I meant with they are not distinguishable. Because you know that the traces, if you look at the traces, they will always have pay, empty set, some kind of drink, pay, empty set, some kind of drink, and the same here, pay, empty set, some kind of drink, and so on. And what does it mean that they are not distinguishable? Well, I just showed you the theorem that said, if I have trace equivalent transition systems, they satisfy exactly the same LT properties. Meaning, there is no LT property that can tell these two transition systems apart. Okay, let's move on one step further. Are there any questions before we go on? Linear time properties, what is a linear time property? What is the satisfaction relation for a linear time property? What are traces? Okay, good. So let's move on. I already mentioned this. Now we're going to basically categorize linear time properties into different classes. And by the end of it, it will hopefully be clear why it's meaningful and important to do that. And the first classes we're going to look at are invariance and safety properties. Now, safety properties, the intuitive formulation or the intuition behind any safety property is it expresses that nothing bad will ever happen. Well, what kind of examples do we have for this? Well, one is mutual exclusion. It says, never is it going to be the case that my transition system enters a state where process 1 and process 2 are in its critical sections. Deadlock freedom, same thing. Never is it going to be the case that I will not have the option to move on in my transition system. And finally, another example for a maybe more intricate safety property is that given a traffic light, you want that every red phase is preceded by a yellow phase. It means that it is never the case that we have a red phase that is not preceded by a yellow phase. So you see that all these properties, somehow you can formulate them as nothing bad will ever happen. Okay? And Leibniz properties are somehow dual to this. They say that something good will happen. An example for this is what we had earlier. This Leibniz property is saying that if a process waits for the critical section, that it will also eventually enter it. It's not about preventing bad behavior or saying this will never happen, but it's about saying that what good will happen or what good needs to happen. And similarly, if you think of the exercise sheet, you want that the dining philosophers eat infinitely often. Okay, so these are examples for Leibniz properties. So let's, forget Leibniz properties for the moment. They will be the topic of the next lecture mainly. And let's come back to safety properties. Now there are 3 examples for safety properties on this slide, and I would argue that 2 of them fall into the same subcategory, and 1 of them is kind of the odd outstander. Why would I say that? No idea? Okay, let's look at these examples. So I would say mutual exclusion and deadlock freedom, they are local properties, right? I can look at one state and say, does it violate my property somehow or does it not? Right? I can look at one reachable state and say, yeah, because this state is reachable, the property is not satisfied. If there is a single state where we have crit 1 and crit 2 in the labeling, it means mutual exclusion violated, or you can forget about it. It will never hold. Deadlock freedom, it means give me a deadlock state, a reachable deadlock state, and just by looking at this one reachable state, I can tell you your property is not satisfied. And this last one, it's somehow different, right? Because it somehow relates different states of my transition system, right? In one state, I have some, for example, the atomic proposition red holding, and then I need to reason about that it was preceded by yellow in some predecessor state or something like this, okay? So the categorization we will use is that the first 2 are called invariants. And it essentially boils down to no bad state, bad in the sense of violating this as a local property, will ever be reached. And this is the first set of subset of LT properties that we're going to look at in detail now. Invariants. And I've already said invariants are somehow local things. And as it turns out, we can characterize invariants just by propositional logic. And how do we do this? Well, first let's talk about propositional logic in our case real quickly. We define it to be every formula that respects this grammar. It can either be true, it can be an atomic proposition, it can be a conjunction of 2 formulas, and it can be the negation of a formula. Well, of course, you can derive a lot of other operators from this, but negation and conjunction are already functionally complete. But you may, for example, in exercise sheets, you can also use the usual Boolean connections. That's fine. Okay, so that's the grammar for propositional logic we're going to use. And now we want to give it a semantics in terms of subsets of atomic propositions. And how are we going to do this? So we're going to define another satisfaction relation, but this time we're defining when does a set of atomic propositions satisfy a propositional logic formula built according to this. So let's take an arbitrary subset of atomic propositions. Then all of them satisfy true, because true doesn't impose any requirements intuitively on the set A. We say that capital A, a set of atomic propositions, satisfies lowercase a, so this is a propositional logic formula, if and only if the atomic proposition is contained in the set. We will see an example in a bit. And probably very straightforward also to you. We say that a subset of atomic propositions satisfy a conjunction of 2 formulas if it satisfies phi 1 and phi 2, so both of them, and it satisfies the negation of a propositional logic formula if and only if, it doesn't satisfy the property itself. Okay, let's look at an example. That's maybe the easiest. So say we have as a set of atomic propositions the set containing A and B. Well, does it satisfy A or not C? So this is a propositional logic formula. Well, yes, it does, because let's look at it more closely. Okay, this is a disjunct, so either one of them needs to be satisfied, so only one of them at least needs to be satisfied. C is not contained in here, so the second part is not true, but A is contained in this set, so we say that this set satisfies this propositional logic formula. And similarly, we have that the set AB does not satisfy this long formula. Well, first of all, C is not in there, so we can forget about the second disjunct here. So let's check the first one. We have that A is in there, but then this formula requires that if we have A in there, we must not have B in there, but B is in there, so it violates the propositional logic formula. Any questions? Okay, now we've defined it for labelings, so sets of atomic propositions, and we lift it to states by saying a state satisfies such a property if and only if its labeling satisfies the property. So again, we just look at the labeling of a state in order to determine whether something holds or not. Okay, so how can we now characterize an invariant? Well, an invariant is a linear time property still. So we call such a linear time property an invariant if we can find some propositional formula, phi, such that we can write this linear time property in the following way. It's the set of all infinite words such that for every position in this word, we have that it satisfies the propositional logic formula. So think about deadlock again. So for deadlock, let's derive a formula. For example, we have the atomic proposition deadlock that we attach to all deadlock states. And then our propositional formula for characterizing these states, it's just deadlock. And then it means the linear time property is the set of all words such that for all the positions, we do not have deadlock in here, for example. That would then express deadlock freedom. Yes?
But for example, a deadlock can be like two states. Each one is infinitely referring to the other state, right?
This is, okay, in my book, I'm not strictly calling this a deadlock, but you're right. You would want to somehow detect that as well. But this is not what I meant with deadlock here. I meant deadlock in the sense you cannot proceed any longer. If you also understand it in the broader sense, then you need to do more work. Then you, for example, would want to express it maybe as a liveness property, saying something good will happen, you will eventually get to some point, right? Because if you then have such a deadlock, it means you cannot go maybe there where you want to go, and then this is violated. But then you would need more properties, other properties. Here I was just referring to deadlock to a state that has no outgoing transitions, for example. Okay, and then if we can write a linear time property like this, we call it invariant, and we call this formula phi the invariant condition of E. So let's look at an example we already had on the slide, mutual exclusion. We can define it, so that was the original definition, saying it contains all infinite words such that at no point in time do we have crit 1 in one of the labeling sets, and at the same time crit 2 in the same labeling set. That was the original definition. That's just linear time property. No invariant yet, but we can come up with an invariant condition phi saying not crit 1 or not crit 2. And if you then take the set of all infinite words such that at every position this formula is satisfied, then you arrive at exactly this property up here. And this is why we call the mutex property as an invariant, right? Because we could characterize it just via propositional logic formula. And there are other things that are invariants as well. For example, deadlock freedom for 5 dining philosophers. The LT property definition would look like this. Take the set of all infinite words, A0, A1, A2, and so on, such that at every position, there is at least one philosopher that's currently not waiting for the fork, maybe, right? And then I would argue this is an invariant again. So what might be the invariant condition here? One possible invariant condition. Yeah, it's very similar to up here. We just say not weight 0 or not weight 1 and so on. So if you take the set of infinite words such that at every position this formula holds, you arrive at exactly this linear time property, which is why this property is an invariant, because we could find an invariant condition that characterizes it. Okay, let's talk about when invariants are satisfied. Right? This is just a definition, repeated definition of an invariant. And if you're talking about invariants, then the following is very easy to see. We say that T satisfies the invariant E, still a linear time property. This is just the definition for the satisfaction relation of linear time properties, meaning this is the case if and only if I can take any path in my transition system and its trace will be included in the linear time property. Well, then for invariance, you can reformulate it such that you say S needs to satisfy, or any state that appears along any path of the transition system T needs to satisfy the invariant condition. And what states appear on any path in the transition system? Well, it's exactly the set of reachable states. So ultimately, you have that a transition system satisfies an invariant if and only if every reachable state satisfies the invariant condition, which is not very surprising given that we said an invariant is characterized by the fact that at every position we have to have that the invariant condition holds. Okay? Does that make sense? Exactly. So let's talk about algorithms for the first time. Now we want to come up with an algorithm that, given a finite transition system and given an invariant, derives whether the transition system satisfies the invariant or not. If it does, we're going to say, yes, everything holds, or not everything, I should say, but your invariant holds. And in case it's violated, we may also want to return a counterexample, an error condition that says, why does your property not hold, right? And because we have the specific setting of E being an invariant, we will assume that we have the invariant condition at our hands. Okay, so first of all, what might a counterexample look like? Well, if we say, or if you can derive that a transition system does not satisfy an invariant, it means there was some reachable state that violates the invariant condition, right? So what we could give as a counterexample is a path going from the initial state to the violating state. And that's simply it, because that gives the designer the feedback, yeah, this trace or this path is in your transition system, and this path violates the property. It explains violation of the property. Okay, let's come up quickly with an algorithm in the last 6 minutes that checks transition systems versus invariance and gives a counterexample along the way. And very trivially or very straightforward, it will be built on regular graph searches. More concretely, we're going to use depth-first search. I'm assuming you all know depth-first search through a graph. Okay, what are we going to do? We're going to look at all the initial states of the transition system, and from every transition system, we're going to perform a depth-first search from this state that looks for states that violate the invariant condition. And if this thing returns true, we're going to talk about the implementation of this in a bit. If it returns true, it means it found a state that violated this, and we can return no, right? Because we know we found a state that violates the invariant condition, property doesn't hold, well, there you go. And if after all these explorations, we have not found a state that violates the invariant condition, we can answer yes, because no reachable state in the transition system violated the invariant condition then. Okay, so our implementation that we'll talk about in a bit returns true if and only if the depth-first search starting from this state as 0 leads to some state that violates, some state T that violates the invariant condition. Now we also wanted to have a counterexample, so a trace that goes from the initial state to a violating state along the way, and we're going to use a stack for this, right? So Initially it's empty, but our depth first search in here, it will make use of this stack and fill it such that if it finds a violating state, then it will say the content of your stack, actually the reversed content of your stack is a counterexample. It's a finite trace, or yeah, it's a finite path going from the initial state to a violating state. Okay, and also for this whole procedure, we're going to store the set of process states. Well, strictly speaking, we wouldn't need to do this, but then it could be that the DFS in here visited states multiple times, and effectively every sub-depth first search here, it needs to track which states were already visited, right? Because otherwise we could get into a cycle and never know that we already explored the states. Yes?
But why would you use DFS instead? Because like you might have infinite.
So we're going to, as I said, we're going to use a set of states that says which states were already visited. So it's not possible that given a finite transition system, you will run into a loop that you do not exit. But you're right in the sense you could just as well use breadth first search. You can use any graph search algorithm that at some point at least has explored everything if it was necessary in order to prove satisfaction of the property. Okay, let's talk quickly about the implementation of the depth first search, starting from state S, looking for a state violating phi. Well, U was the set of states that we already visited. So we're only doing some work if the state S was not yet explored, right? Otherwise, we can just skip and say, sorry, but we have not found such a state. If we still have to process S, well, then one thing that could happen is that S already violates the invariant condition. Well, if it does, then we return true to indicate, yes, we have found a counterexample. If, however, S satisfies the invariant condition, then we might need to go deeper into our transition system. And so we record S as being processed and recursively start the DFS from all successive states. Right? I mean, this is what depth first search is all about. And still keeping in mind that we wanted to produce a counterexample in case we found a state that violates phi, we have two stack operations. Initially, when we start the DFS from state S, we push it onto the stack, and when we've dealt with it, we pop it from the stack. Right? And note that by pushing here and then going deeper, and at some point returning true because we found a state that violates the invariant condition, it might be that we return up to the highest level and still have a non-empty stack pi. Okay? Okay, let's not go through this in detail because we have 1 minute left. Let's talk briefly about this transition system as an example. It has 3 states labeled with A and 1 with empty set, and our invariant condition is A. And we have that these 3 states satisfy A and T does not satisfy A. And let's quickly step through our algorithm, starting the DFS from S0, looking for a state violating A. Let's say we first go to S1, because that's the first successor. We put it onto our stack and recursively descend. So from S1, we're going to call again depth first search starting from S1. But we directly notice, well, S1, we've already visited that, so we can pop it from the stack. Then we have dealt with all successors of S1 here, so we can pop this S1 from the stack and are at the highest level again. Then we look at the second successor of S0, so performing a step down from S0 to S2, push S2 onto the stack, go one step further, call DFS looking for a state violating A from T. And then we see, this state T violates my invariant condition, so I will return to the highest level, and you see on the stack you have exactly the reversed counterexample saying that if you go from S0 to S2 to T, it gives you a trace to a state, namely T, that violates the invariant condition. And so you can say your transition system, and in particular state S0, violates the property always A, and the arrow indication is contained in the stack. And thank you very much for your attention. See you next week.